In our work, we develop a framework for explaining black box classifiers. We propose that an explanation should be based on principles of causality. An aspect of the data explains the black box's action if changing it, while keeping all other aspects constant, produces a corresponding change in the classifier output. These aspects have a large causal effect on the classifier output. In this stylized example, our black box classifies based on color. Changing the color of this orange, while keeping everything else constant, changes the classifier output, but changing the shape of the orange doesn't. Our goal is to learn these aspects, which we'll visualize using examples. To find data aspects that have a large causal effect on the classifier output, we use a generative model framework to learn a low-dimensional representation of the data. The key to our approach is that we learn this representation in such a way that a subset of the latent factors, the factors denoted alpha, have a large causal effect on the classifier output. Our learning strategy looks like this. We learn a generative map that maximizes the causal effect of the alpha on the classifier output y, such that together the latent representation alpha beta is a valid representation of the data. To determine the form of this causal effect term, we define a causal model relating the low-dimensional representation, data, and classifier output. In the paper, we describe 3 principles this model should obey, which lead to this causal graph. We then apply, again based on principles we outline in the paper, the information flow metric of I and Polanyi. Because we design our model with independent learned latent factors, this metric simplifies to mutual information. We see the simplicity as an advantage, but note that even if we did have non-independent latent factors, we could accommodate it naturally using I and Polanyi's definition of information flow. In the paper, we also discuss some variants of this metric that are also consistent with the principles we outline. We first analyze our model with simple classifiers and a linear-Gaussian generative model. In the paper, we provide some basic theory that helps us understand things like when we should expect our learned factors to correspond to semantic concepts, and the effect of our objectives tuning parameter. These example results show sample explanations generated by our framework for a classifier trained on the MNIST digits 3 and 8. Each row shows a different sample of the training set. Moving along the horizontal axis shows how the image changes as a latent factor is varied. Observe that the learned causal latent factors control the classifier relevant features, like the curves on the left side of the digit. This is reflected in the changing colored borders denoting classifier output. The non-causal latent factor, on the other hand, controls stylistic features like thickness and rotation, but doesn't affect the classifier output. The core contribution of our work is a framework for generating explanations for black box classifiers guided by principles of causality. In effect, we learn a classifier supervised disentangled representation of the data that separates classifier relevant and classifier irrelevant features. Thank you, and we'd be happy to hear from you if you have thoughts or questions.